All right, we're back with section B of chapter 9 on predicate logic. And in this section, what we want to do is introduce 4 new rules of inference. Now, these are like your implication rules, as it were, but they are unique to predicate logic. And these 4 rules are all expressed using 3 words: universal, instantiation, generalization, and existential. Sorry, that's 4 words. But the point is, you got rule number 1 is universal instantiation. Rule 2, universal generalization. Rule 3, existential generalization. And rule 4, existential instantiation. Now pause. You already know what the words universal and existential refer to. Universal refers to a universally quantified statement. So those rules, number 1 and 2, that begin with the word universal, are going to be rules that you can use in relation to universally quantified statements. Now, they're going to do opposite things. One's going to instantiate and one's going to generalize. The same idea holds true, though, with the existential rules 3 and 4. Those are rules that have to do with existentially quantified statements. Now, what these rules let you do is 2 things. They let you instantiate and they let you generalize. Here's kind of a crude, simple way to think about what instantiation is. Instantiation lets you take a quantified statement and get rid of the quantifiers. And that's going to be useful to you. Generalization is going to let you take a non-quantified statement, function, or proposition, and is going to let you quantify it. So instantiation gets rid of quantifiers. Generalization puts things into quantifiers. That's a crude, easy, simple way of thinking about it. But there's some different nuances that apply to these different rules. So instantiation is what I just explained it to you. When instantiation is applied to a quantified statement, that quantifier is removed, and every variable that was bound by the quantifier is replaced by the same instantial letter. Now, what is an instantial letter? An instantial letter is either a variable or it's a constant. And that's what you use when you instantiate quantified statements. Let me give you some examples, starting with universal instantiation. So universal instantiation removes the universal quantifier. So here's a valid application of it. Let's say you've got this universally quantified statement. For all x, if x is p, then x is L. Now, you can apply the universal instantiation rule to this line and validly derive one of 2 conclusions. Basically, you drop the quantifier and you can replace the x with either an instantial letter, either with a constant, like in this case, you could get if s is p, then s is L, or with a variable. If x is p, then x is L. Now, you can make either one of these moves, and there might be tactical advantages of using either a constant or a variable, depending on the proof you're trying to work and the conclusion you're trying to get to. Here's what you don't want to do. You don't want to, what you do have to do is you have to replace each occurrence of the bound variable with the same instantial letter. You can't like start mixing and matching. Oh, use, S for this one X and, R for another or something like that. So you can't do that. Also, you cannot, like this is a weird move that they made here. You can't go from this quantified statement to another quantified statement and stick in constant. That doesn't make any sense. For one thing, this statement right here, for all x, if s is p, then s is L, that doesn't make any sense, because what you should have in a quantified statement is only variables. You don't ever have constants in there. So you can't make that move at all. But certainly when you universally instantiate, you got to replace both x's with the same letter. You can't do like s and r or s and x. It's got to be the same consistency. All right, next rule is this one. Universal generalization. This lets you move in the opposite direction. So the first one took a universally quantified statement and it dropped the quantifier. Let's say you want to get a quantified statement. Here's what you do. You can apply the universal generalization rule to a statement function like this one that includes only variables and actually the same variable, and you can universally quantify it. So if you've got if y is p, then y is t, then you can conclude by universal generalization for all x, if x is p, then x is t. And truthfully, you could have said for all y, if y is p, then y is t. It doesn't really matter which variable you use as long as you're consistent. Now, why is it that you can move from this kind of statement function to this universally quantified statement? Well, because if you've got something that holds true, for any given variable, it's not specific to like one particular item, then you can universally quantify it. Say, hey, this holds true for all. Now, here's some things you don't want to do. Here's how to screw this rule up. You can't move from, say, if y is p, then y is t, to a universally quantified statement that's got mixed variables in it. Look what they did for all x. If x is p, then y is t. Don't do that. You got to make them both x or both y. You got to be consistent. Also, here's another thing you can't do. You can't universally generalize from a statement function that involves only constants, or a proposition that involves constants, to therefore something that holds true of all individuals. So if I say, if A is P, then A is T, I can't conclude on that basis that therefore for all X, if they're P, then they're T. Because A is a constant that names a particular item. It's like Abe Lincoln. If Abe Lincoln is president, then Abe Lincoln is tall. Well, just because that's true of Abe Lincoln doesn't mean it's true necessarily of all individual items, period. It might be unique to him. So that's why you can only go from statements, functions that are true of kind of variables, but not of specific items like this. Next, existential generalization. So this allows you to introduce an existential quantifier from either a constant or a variable. So let's say you've got a statement function like this, y is m. Well, you can then existentially quantify that and say there is some x such that x is m. Or you could have said, there is some y such that y is m. That's fine. You can also go from a statement about an individual and you can do an existential generalization from that. So this is a way in which existential generalization is different from universal generalization. If you know that, say, Abe Lincoln is male, then you can conclude from that there exists some x such that x is male. Because if it's true of one, it's true of some, right? That's what some means. So you can existentially generalize from stuff that involves variables or that involves constants, either one. Now, here's what you don't want to do. You can't, again, mix your variables up, right? So if you've got my and ry, you can't go, there exists some x such that x is m and y is r. You got to be consistent. And then finally, we've got existential instantiation. And this is kind of the mirror of universal instantiation. It's got an asterisk though. So this lets you go from a existentially quantified statement, like there exists some x such that x is b and x is k. What you can derive from that is you can put a name on the something that we're talking about. You can say, let's say it's C, Charlie. So Charlie is B and Charlie is K. So you notice there that you're using one of the constants, A through W. You're not using a variable X, Y, or Z. And that's the only thing you can do when you do existential instantiation. You can't go from there exists some X such that X is M and conclude X is M. It doesn't work with variables. Or you can't conclude to variables. You have to conclude to a constant. You're naming the particular individual of which, a particular individual of which this existentially quantified statement is true. Let me show you Another, and okay, by the way, the same old, well, here's another misapplication of existential instantiation, okay? Let's say that you've got two existentially quantified statements, right? Like this. For some x, x is b, and for some y, y is k. Now, you can apply existential instantiation to that first line for some x, x is b, and you can derive Charlie is b, CB. That's fine. So far, so good. But what you can't do then is to take another existentially quantified statement and give it the same name. So you can't say for some y, if y is k, that therefore Charlie is k, because you don't know that the same individual that is b is also k. Each of these just individually says something is b and something is k. It doesn't say the same thing, the same Charlie is both of those. And this leads us to a really important restriction on the existential instantiation rule. If you establish a constant before you have used existential instantiation in the proof, then you cannot use that constant again with existential instantiation. You have to assign the existential instantiation a different name. So for example, if I've got, just like I said, here's the problem. What you would have to do is to say, okay, Charlie is B, C is B, and then you'd have to say like D, Danny is K, so KD, because you're specifying then, hey, they might not be the same items that have these predicates. In other words, you can't use use existential instantiation and give a variable a name that has been used in the proof on any line of the proof prior to the existential instantiation. And you also can't use the name of a constant that appears in the conclusion. So here's a tip, right? Let's say you've got a proof and it's got existentially quantified premises and it's got universally quantified premises. You're usually going to want to use existential instantiation first. Here's why, because there's no restriction on what name you can give it. So let's say you want to prove, SA, right? And maybe this is not the final conclusion, but and you've got premise one for all y, if y is p, then y is s. And premise two, for some y, y is p. Well, you first want to apply existential instantiation to premise two, and you can get PA. And then you want to apply universal instantiation to premise one. And now you can use A again, because you don't have that restriction with universal instantiation. When you use universal instantiation, you can give the universally instantiated statement functions any name you want, including one that's been used before. So you can make this, if A is P, then A is S. Now, why is there that difference there? Because this is universal. Everything that is P is S, including A. So that's why different rules apply. And then you can conclude from both of those, okay, by modus ponens, I can get SA. So if you know you're going to need those, instantiate the existentially quantified statement first, because you've got a wider range of options of what names you can use. All right, this brings us to tactics and strategies. So as always, we want to look at the conclusion we're trying to reach. And if what we're trying to reach is say a universally quantified conclusion for all x is such and such, well, we're probably going to be using universal generalization to get that universally quantified conclusion. And if we're starting off with universally quantified premises, then we're probably going to have to be using universal instantiation to drop those, take the quantifier off the premises, and then we can apply our implication rules, our replacement rules, and we get the conclusion we need basically, and then we can generalize it. We can quantify it again to get that quantified conclusion. And again, the same goes for, if we're trying to get an existentially quantified conclusion, we're going to use existential generalization to get there. And probably if we've got premises that are universally or existentially quantified, we're going to first instantiate them, apply our implication and replacement rules, and then use our existential generalization rule to get to the conclusion. That's actually the basic shape of how these proofs tend to work. So yeah, you're going to use universal UI on universally quantified premises to instantiate variables and constants, in EI in the parallel situation. Remember this though, predicate logic rules, those 4 rules we've learned today, they only apply to entire lines. They don't apply to partial lines. They're like the implication rules in that respect. You can't use an implication rule on just part of a line. You've got to use it on the whole line. Tactically, you might want to use simplification, and you might use a lot of things. So let's try an example here. So here's what we got. Premise 1, for all x, if it's s, then it's t. Premise 2, for all x, if it's t, then it's p. Now pause there for 1 second and listen to what I'm saying. Everything that's s is t. If it's s, then it's t. And if it's t, then it's p. What implication rule do you feel like we're in the neighborhood of right now? That's right, hypothetical syllogism. It seems like we can apply hypothetical syllogism, and we can, but remember, we can't apply hypothetical syllogism or any of our other implication or replacement rules to stuff that's to these statements that are bound by a quantifier. So we're going to have to instantiate these first, then apply our rules, and then generalize them again, bring the quantifiers back in. Our third premise here is A is S. So we know that we can get to, if S is T, then it's P through like hypothetical syllogism. And we know that something is S, therefore something is P. And that's basically the conclusion we're getting to, something is P. Okay, so I could work this backward for you, and I would like to, but let me just pull up the whole answer here. So first of all, we're going to drop the quantifiers off of premise 1, and we're going to use universal instantiation to do that. Now we could have put variables like x in here where the a's are, but we want to put the a in because we want to be able to apply this line to 3, and we want to be able to talk about a's, and so we've got to have a consistent letter that we're talking about. If we know that we're going to need to apply this to a's, and you want to instantiate it as an a, not as a variable, not as some other name. We're going to do the same thing to premise 2, right? Let's apply that. So if you apply universal instantiation, you get if A is T, then A is P. And now we can use hypothetical syllogism on lines 4 and 5. Sorry, they use modus ponens. It doesn't matter which order we do it in, really. But so we know that S is A, and if SA, then TA. Therefore, by modus ponens, we've got TA. And now we can do the same thing to lines 5 and 6, right? Apply modus ponens, and we get PA. Now is when we're going to generalize. We're going to bring the quantifiers back in because we've got to the basic place we need to be. We know that something is P. Abe Lincoln is P, or whatever. And if that's true, then if it's true that Abe Lincoln is P, then something is P. And that's where we can use existential instantiation. If A is P, then for some x, x is P. And it's good that we had an individual constant here, not a variable, because when you use existential generalization, it has to be from a constant. It can't be from a variable. Well, congratulations. You've just done your first proof in predicate logic. I hope you're fully successful in doing your homework as well.